Hello everyone, let's start the new section. The previous two chapters dealt with the electrostatic, thus with the charge at rest. With this chapter, we began to discuss charge in motion, or electric current. This is the basis of the study of magnetism later. Electric current is a charge in motion, the directional moment of the electric charge. The carriers of the charge can be physical particles like electrons, protons, ions, or holes, which may or may not be attached to larger objects. Atom or molecules, here we are not concerned with the nature of the charge carriers, but only with the net transport of the electric charge their motion causes. So, in the conductor, how is the current formed? First of all, there are charges that can move freely in the conductor. Next, an electric field must be maintained in the conductor. The movement of the electric charge in the conductor indicates that there must be an electric field in the conductor, which is different from the situation where the electric field strength in the conductor is zero when the static is balanced. The electric current I in a wire is defined as the amount of charge that flows through the cross-sectional area of the wire in unit time. The magnitude of the current I is the amount of electricity passing through the certain cross-sectional of a conductor per unit time. The current has a direction, which is defined as to be directional of the flow of positive charge. The SI unit of the current is a coulomb over second, which is called an ampere. A more general kind of current or charge transport involves a charge carrier moving around in the three-dimensional space. Current intensity has a rough description of the current. For example, for conductors with unequal cross-section cannot reflect the current flow at different cross-sectional and at different position on the same cross-section. To describe this, we need the concept of the current density. Let's introduce the current density vector J, a physical quantity that describes the magnitude and the direction of the current at each point in space. The current density at a point in the conductor is numerically equal to the current intensity per unit area perpendicular to the quantitative moment direction of the positive charge at that point. The vector J at any point is oriented in the direction that a positive charge carrier would move at that point. The distribution of current density vector J forms a vector field. We call it current field. In the current field, the current intensity through area element ds is di. Thus, the dot product J and ds. Di is the flux of the vector J over that surface, where theta is the angle between them. In general, the current intensity passing through any area S can be determined by the integrating the current density over the surface and this equation. In general, for a particular surface which need not be plane that cuts across a conductor, di is the flux of the vector J over the surface, or di equals to J dot ds, where ds is the element of surface area and the integral is done over the surface. The vector dA is taken to be perpendicular to the surface element such that J dot dA is positive, giving a positive current I. From this expression, we can see that current intensity is the flux of the current density over any particular surface, which need not to be plane. This is a relationship between current density J and the current intensity I. The movement of charge can form an electric current and also cause the change of the space charge distribution. Taking a closed surface S in the current field, there will be charges flowing in and out of the S surface, and the charge in the S surface will change accordingly. Taking a closed surface S in the current field, then charge flows in and out from surface, and the charge in the surface S changes accordingly. According to the law of the charge conservation, for any closed surface, the net amount of the electricity flowing out of the S in a unit time should be equal to the decrease in the amount of the electricity in S. The equation is called the continuity equation of the current. Thus, the flux, the surface integral of the current density over a closed surface is equal to the rate of the charge reduction in the surface. Current lines oriented where the positive charge decreases and end where the positive charge increases. When the charge in the surface does not change with time, thus the current flow in and out from the closed surface is equal. There is no charge accumulation in the surface, and the current passing through the closed surface is constant, so it's called the constant current condition. The current line passes continuously through the volume enclosed by the closed surface and cannot be interrupted anywhere. It's always a closed curve. In this case, the magnitude and the directional of J and each point in the current field do not change with time, which is called steady current. The field associated with a steady current is called a steady electric field. For a steady circuit, there's an electric field in the conductor. The steady electric field is produced by the charge distribution that does not change with time. And a steady current circuit must be closed, which is also known as Kirchhoff's first law. In a conductor, what's the quantitative relationship between current and the electric field? Consider the smaller cylinder in the conductor. The current through the planar element ds is di. The voltage at both ends of the small cylinder is du. The length of the small cylinder is dl. The current through ds is di. Thus, potential difference du divided by the resistance R. From Ohm's law, we express R in the differential form where rho is a resistivity, and then we get this expression in which di over ds is current J, du over dl is electric field E, sigma is conductivity. Then we get the relationship of the J and the E, that's the differential form of the Ohm's law. Considering that J and E are in the same direction, we express it in the vector form. It describes the point-by-point relationship between the electric field and the current distribution in the conductor. Electrostatic force cannot maintain a constant current. To maintain a constant current, there must be a non-electrostatic force. An external energy source is required by most electrical circuits to move charge through the circuit. The circuit, therefore, must include a device that maintains a potential difference between 2 points in the circuit, just as a circulating fluid requires an analogous device, like a pump, that maintains a pressure difference between the 2 points. Any devices that can provide non-electrostatic force is called a source or a seat of the electromotive force. Its abbreviation is EMF. Inside the source, the non-static force overcomes the static force to move the positive charge from the negative to the positive, while outside the source, the static force pulls the positive charge from the positive to the negative. In a source-containing circuit, the differential form of the Ohm's law is expressed in this form, where Ek represents the non-electrostatic field intensity, which is a non-static force applied to the unit positive charge. The electromotive force describes the capacity of the power source to do work. So let's calculate quantitatively. When the charge Q is moved from the negative to the positive through the inside of the source, the work done by the non-static force of source is a path integral of the Fk. In the process of the moving unit positive charge from the negative to the positive through the source, the work done by the non-static force is defined as the electromotive force. If the electromotive force EMF exists in the entire current loop L, the EMF can be written in the form of the loop integral. It represents the work done by a non-electrostatic force per unit positive charge around a closed loop. That's all for the section. Thank you for your attention.